Okay. Oh, alrighty. So just for I guess for folks, or if someone watches this at some point that has not seen this before, I'm a busy human because I have my head in a book, basically all day, or I'm avoiding having my head in a book almost all day because of this test that I have to take. And this test is my topology PhD qualifying exam. It's majorly over point set topology and other like set theory-esque style things that relate to topology, because that's what my math department focuses in the realm of topology, and or some topological dynamics stuff as well. And so I've been streaming, doing some of these problems that come up on these quals because um, I would rather be making videos, but this is all I can do currently. And part of this channel is sort of documenting my PhD experience. And since my life is relatively boring right now because I just do this um, all day, every day, on repeat, um, this is what I'm putting on this channel right now. Yeah, that's how we're doing. Hello, how's it going? Um, so I guess okay. So I'm just gonna start working through stuff, and we'll see how this goes. Hopefully, this goes smoother than it did the last two times. But it is what it is. If I make mistakes here, that's fine. It's happening now, and it's not happening when the committee reads my submission, right? So my focus, okay, well, so what I do currently, or what I think about currently, is more in the realm of topological dynamics. I'm really interested in in representations of dynamical systems with symbolic dynamics, and then also thermodynamic formalism. So those are like the areas that I am reading more about currently, and one of those will probably be my research focus for my thesis. So I have a few topics that I'm working through currently, but again, most of that's on hold because my life currently has been just do topology problem. So yeah, I'm gonna get started. So this is for my own purposes. I think this is still it's still August, right? Yeah, this is an August test. This is 2020. Oh, I'm gonna have to turn that off. I'm listening to the Octopath Traveler soundtrack in the background because it gives me hope. Um, but some of the songs on there are just like a little distracting. Um, of course, I can't play it on stream because it's licensing and stuff, right? But it's just sometimes it's just pleasant study music. So the first problem is just here's like what the definition of this thing that they want me to use. So a T1 space um, is, oh, can I write good this morning? That would be great. So a T1 space is perfectly normal, or perfectly regular rather. Or no, it's perfectly normal. Yeah, I was right. Perfectly normal. Um, if for any, oh, for any two disjoint closed sets, A and B, um, there's a continuous function from 0, 1 or from the space to 0, 1, rather. Where f inverse of 0 is equal to a, and f inverse of 1 is equal to b. And then the proposition is show that a T1 space is perfectly normal if and only if the space it is T4 and every G delta, every closed set is a G delta set. So if it is T4 and every closed set is G delta. So that just means that every closed set is a countable intersection of open sets. So this is actually, I think this is probably one of those problems where I'm the most comfortable, which I guess I say that now, but we'll see how this goes. At least in my brain, like I have a pretty good roadmap of how to do this. So for the forward direction, things are pretty okay. So let A and B subsets of X closed, and A intersect B equal to the empty set, then since X is perfectly normal, there exists F from X to 0, 1 such that F inverse of 0 is equal to A and F inverse of 1 is equal to B. So well, first off, so A and F inverse of the set 0 intersect F inverse of the set 1. Oh, what am I doing? I just need to show that. What am I doing? Okay, so it's just so let 0 less than epsilon less than 1 over 2 be given, then A is a subset of F inverse of the interval from 0 to epsilon open, and this is open as 0 to epsilon is open in the subspace topology on 0, 1. And then B is a subset of F inverse of 1 minus epsilon to 1. And this is also open as 1 minus epsilon to 1 is open and 0, 1 standard. So note that, or rather, also we start there. Also note that the intersection of these two things take that inverse of 1 minus epsilon to 1 is going to be equal to, well, pre-images respect intersections. And so then this is going to be empty. Or it's going to be the pre-image of the empty set. which is the empty set. Hence, X is T4. To see that every closed set is G delta, this is not terrible either. So what you do is you just look at open intervals that converge to just a singleton zero and on the left and on the right. So it'll be like this. So let n with it let for every n with an n, or rather for every n with an n, let u sub n equal to, well, 0 to 1 over n, and b sub n equal to 1 minus 1 over n to 1, then for every n with an n, 0 is within u sub n, and 1 is within bn. I mean, well, yeah, so I guess the gist of it is that just then the intersection over n with an n of un is equal to the singleton 0, and then the intersection over all n with an n of vn is equal to 1, the singleton 1. So f inverse of un, this collection of sets and this collection of open sets are such that what you get is that these just intersect down to be a and b, because f inverse of the singleton 0 is going to be a, and f inverse of the singleton 1 is going to be b. So such that yeah, okay. Why did I zone out for a second? So the intersection over all of these things, it's going to be equal to un, which is equal to the preimage of the singleton 0, and that's going to be equal to a, and then similarly oh, my head's not coming in. Cool. Okay. Similarly. Hello. How's it going? Um, the intersection over all n with an n of this stuff is equal to b, because it's the same thing from the line up. It's just that it's vn's and then the singleton 1, and then the preimage of the singleton 1 is b. So t1, so since x is t1, or rather, I don't here. Hence x is since x is t1, it is t4, right? So this first part was showing that it was normal, and then down here is showing that every closed set is a G delta set. So every set and we're done with that direction. So that was the forward. That was forward. So backward is showing that if a space is T4 and every closed set is a G delta set, then it is perfectly normal. So how this works is this is an application of, I think it's Eurozone's lemma, right? So for the backwards direction, let A be equal to the intersection n within n un and B equal to the intersection n within n bn bg delta, or well, be closed sets of the T4 space X. So I can write them as those intersections because they are G delta. And so then by Eurozone's lemma, or well, I want to be careful about this. So um, then oh, be disjoint. I want them to also be disjoint. Be disjoint closed sets. T4 space, then A is a subset of Vn complement for every n within the naturals. Is that what I want to do? Yeah, that's what I want to do. Yes, okay. So A is a subset of Vn complement for every n within the naturals, and so by Eurozones, and I also should say this for B as well, because B has a similar property, right? So A is a subset of Vn complement for every n, and B is within Un complement for every n. So um, by Eurozone's lemma, there exists an f sub I and g sub I, which go from the space to 0, 1, because it'll be that f of, yeah, this is fine. Okay. I'm going to also call them, I'm just going to keep it the same index so I don't have to keep flipping around. So fn, gn from x to 0, 1, such that fn of a equals 0, fn of b and complement is equal to 1, and and then gn of b is equal to 0, gn of u and complement is equal to 1. We then define oh, and these are continuous. Yeah, so continuous. I need to say that anywhere else. I think I'm good. Yeah, I think so far I haven't used continuity. Perfectly normal. Yeah, and perfectly normal, there is f, and that should be a continuous function. Because that's just what the definition is. And do I say in the definition there exists f, a continuous function? Okay. So, says Eurozone's lemma gives you the opportunity to make a function where the forward image is zero, but it doesn't tell you that the pre-image of 0 is just that set, or the pre-image of 1 is just b. So I need to make a function out of all of these functions, and I'll make another function out of those functions. So or rather define f sub a is going to be the sum n within the naturals of, hold up, I need to put in an x. It's going to be equal to the sum n within the naturals of fn of x over 2 to the n, and then fb of x is going to equal to the sum n within the naturals of f, or not f, but gn of x over 2 to the n. So each of these is a uniformly convergent sum of continuous functions, which is going to be continuous. So each fa and fb is a uniformly convergent sum of continuous functions and is thus continuous and then we're going to define one more function. So define then how far am I zoomed in? Yeah, we're good. So define then f of x is going to be equal to f of a over f of a plus f of b. So continuity here is a little less transparent, even though I think this arguing these two are continuous is like something that is not immediate if you haven't had analysis before. This function is a little bit weirder but it's not hard to show that it's still fine. So this is a rational function. So note that f is a quotient. I'm just going to say a rational function. I don't want to say rational. I just want to say quotient. Quotient of continuous functions where the denominator is never zero, because if you, it's how the denominator works, right? The only way that these two functions are zero is if you are in, so you have to be in A for every single, that's not what I want to say. If they're, yeah, so I don't, that's not what I want to say, but in order for each of these things to be zero, each one of these things, each one of these fn's or gn's needs to be zero, which means that you need to be in the preimage of that thing for every single x. Their preimages could overlap. Where is it non-zero? There is, I think this pops out in a second. Let's see. Where f of a of x plus f of b of x does not equal 0. To see this, just prove it then. This if f of a of x plus f of b, or f sub b of x is equal to 0, then fn of x is equal to 0 for every x within, for every n. And so same thing with g, and g sub n of x is equal to 0 for every n within the naturals, which means that x is not within, oh yeah, so x is within a and b, right? So x is within a and b, which is equal to the empty set by supposition, which is a contradiction. So these things are never 0. That's not what I want to say either. It's not that the pre-image 0. Hold up. That's wrong. This is wrong. I need to be careful about how I construct the cover or construct the G delta set. Do I need to do that? Let's see. It's T4. So it's intersection of those things and B. I am using a Wacom tablet. We are disjoint close, and A is a subset of B and complement. Oh, yeah, I need to start with a B complement as one of these things. The problem. Yeah. So this is the intersection of this intersection of strengths. Then A is a subset of that for every n. There's a function continuous such that this is true. So Fn of A is equal to 0. Fn blah blah. So this is equal to 0. Then F of A. Okay. Then F. Oh. Okay. I'm just gonna argue that this thing is 0 only when x is within A, and this is 0 if and only if x is in B, I think is what I need to do first, because this is the right thing to look at. I just need to be a little bit more descriptive about what I'm doing. I think be fine. Okay. So, oh, I need to move you too. All right. Continuous functions and is thus continuous if fa of x is equal to 0, then f. Oh, okay. Okay, it's fine. Okay, so then x is within, or I don't jump there. So then the sum fn of x over 2 to the n is equal to 0, which means that fn of x is equal to 0 for every n within the naturals, which means that x is within the complement, the un, where is it? Or vn complements. So yeah, it's in the vn complement for every. So x is within vn complement for every and within the naturals, which means that fb of x does not equal 0. Oh, that's not what I want to say. I want to say that it's not in B, right? So the VNs are what give you, the VNs are what intersect down to B, right? So if you're not in any of the VN complements, then you're definitely, if you're not in any of the VNs, then you're definitely not in B. This means that X is not within B, which implies that FB of X does not equal 0. Define then f of x is equal to f of a x over f of a x plus f of bx. That f is a quotient of continuous functions where f of a is plus f of b of x is not equal to 0. To see this, if this is the case, well, these are positive, right? So note, yeah, so if these are both positive, yeah, so if this thing is equal to 0, since um, f a and f b are positive real valued functions, fa of x must equal fb of x, which is equal to 0, but this cannot occur. So now the claim is, so claim is that f inverse of 0 is equal to a, and f inverse of 1 is equal to b. So and this would be the function that gives you your perfectly normal property. So how does this work? Proof of claim, if x is within f inverse of 0, this happens if and only if f of x is equal to 0, which happens if and only if f of a of x over fa of x plus fb of x is equal to 0, but that's if and only if fa of x is equal to 0. But this only happens if x is not within b in complement and bn is within. Did I not use the disjoint closed sets of a T4 space? They can be separated by open sets. Yeah. I didn't use T4 here. Why did I not use T4? I should have used T4 at the beginning. So I could, yeah, I can just make sure that, so the T4 part, okay, I'm gonna write this off to the side because this is what gives you all of the mobility of this proof at the end, I think. So because, so here, go like here. Since x is T4, there exists a u prime and v prime such that a is a subset of u prime and b is a subset of v prime. So what you can go ahead and do, so we may replace un with un intersect u prime. Oh, that, and u prime intersect v prime is equal to the empty set, and vn with vn intersect vn prime. So I'm just saying that I can assume that these things that intersect down are disjoint from, um, like, so if you're in a un, then you are disjoint from v. So in particular, this means that, what does this mean? Yeah, this is fine. Should be easy. F of x is equal to 0, f a of x is equal to 0, so f of x is equal to 0, which means that the the sum of all of these things, fn of x to the n is equal to 0. And this is if and only if x is not within I'm separating closed sets. Oh, did I do this backwards? What am I doing? I need to separate disjoint closed sets. So I don't know what I did. This is okay. This is why we do this now. So then A is a subset of B n complement and B is a subset of UN complement. So it's not that Eurzone's lemma applies to disjoint closed sets. So I just mixed these two things up here, which is why this was hard. So it's this UN complement. It's the thing here. And this should be VN complement. Because this is what happens with Eurozone's lemma. We have an A and a B, and we have an open set that contains A, because this is one of the UNs, and then its complement is then a closed set. So this is UN complement. So with Eurozone's lemma, I can take A and I can send it to 1, and then I can take all of the complement stuff. So oh, I don't want to do that, but just I can take UN complement and I can send it to, I did this backwards again, because that's just how we're doing today. 0 and 1. Okay, so that's fine. Okay, so this is UN complement. Did I screw anything else up along the way? So okay, so then this is equal to this. So fn of x is equal to 0 for every n within n, which implies that x is within so x is not in equal to 0, which means that x is within it's not in UN complement. That's what I want to say. It's not in UN complement. Hello. X is not in. UN complement for every n within n. But that means that x is within UN complement for every n within n, which means that x is within the intersection of n within n. Oh, get rid of the complement. So x is not within UN complement, which means that for every n within n, which means x is within UN for every n within n, which means that x is within the intersection of all the UNs, which is equal to A, which is disjoint from B. So FB of x does not equal 0. There we go. And then we define that function, and then it's the quotient, and it does of continuous functions where the denominator is not equal to 0. And then I don't need to see this if because I just showed it above. And then, so we have the by function, this cannot occur. So f inverse of 0 of A, f inverse 0 of 1 of B. This goes to 0, this here, that means that. So this means that the x is not within, it's not within UN complement for every n within n, but we just saw that that means that x is within A. And then for the other side, right, if x is within f inverse of 1, this occurs if and only if f of x is equal to 1, which is if and only if f of a of x over f a of x plus fb of x is equal to 1, but that's if and only if fb of x is equal to 0. That's if and only if the sum of the gn's is equal to 0, but that's if and only if x is within Vn complement, or not within Vn complement for every n within the naturals, but that's if and only if x is within the intersection over n within n of the Vn's, which is equal to b. And so hence x is a perfectly normal space. So f from x to 0, 1 is such that f of, what is it? It's f inverse of 0 is equal to A, and f inverse of 1 is equal to B. Hence, x is, or thus, x is perfectly normal. And so and that proves the claim. They did both directions. Okay, so not unsalvageable, but yeah, that was kind of not great. It could have been worse. Okay. Oh, and another one. And then let's block out some more stuff so I don't have to do it later. This is what number 2 or 4. This is another like definition and improve something about it problem. So X is a sigma compact. If and only if X can be written as the union. Who grades this stuff? So this is like, I'm not doing my homework, but in terms of like how quals work, at least where I'm at, and most other places that I've heard of how this works is that there's a committee for the subject, and then they vote on a pass fail of whether or not you passed or failed that exam. Some places are more particular where they go ahead and say like, oh, this is like where everyone's going to grade it, and then if you get like a 70, then it's a master's pass, and if you get like an 85 and up, it's a PhD pass or something like that. But at least where I'm at, it's voted on by committee whether or not you pass this exam or not. So X is sigma compact if and only if X can be written as the union of countably many compact sets. Yeah, I mean, theoretical mathematicians do this all the time. This is what I read all day, almost every day. So, in order to prove new things. So, it's the union of countably many compact sets. Then, oh, compact subsets. That's what I want. And then I want to show, so prop is show that the product of finitely many sigma compact spaces are sigma compact but a product of infinitely many sigma compact spaces need not be sigma compact. So my area of interest is in topological dynamics, and so I look at currently the things I'm interested in that area are thermodynamic formalism and symbolic representations of dynamical systems. So my PhD thesis will be something in that realm, hopefully. And then yeah, so that's I think that's my hyper specific focus at this point. However, I have a topology qual, and so that's why I'm doing topology problems, because there's a test on this point set topology stuff that determines whether or not I can go and do research. Would you doing any analysis QE practices as well, or have you any context recommended to study for real analysis of complex analysis? So, I actually passed my real analysis qualifying exam last fall. So I don't have to do that again. And the reason I'm doing this online currently is because part of this channel is documenting what I do in my PhD. And since my summer has been very boring and I don't have time to be creative, um, I figured it's still worth like documenting that this is what I basically do all day is I just prove statements like this. Uh, and so for text recommendations for real and complex analysis, for at least real analysis, because they were separate quals where I'm at. Um, for analysis, we used Royden, and Royden, although it's like a hard textbook, it's my favorite. It's like my favorite analysis textbook now. So I would 100% recommend Royden's analysis, real analysis text. Uh, for complex analysis, complex is one of those things where it's like I'll get better at it as it comes up with respect to my research. So, um, but yeah, thanks. But yeah, so complex analysis, I am not as strong in complex analysis as I am in like real analysis and measure theory and topology stuff. So I'm not the best resource for a recommendation there. So, okay, so X is sigma compact if and only if X can be written as the union of countably many compact subsets. And then the proposition to show that the product of finitely many sigma compact spaces are sigma compact, but a product of infinitely many sigma compact spaces need not be sigma compact. So proof. So proof. So it suffices to show that I can do it for the product of two. Um, show that one can that the product of two sigma compact spaces is sigma compact. So let x and y be sigma compact. Then, right, so they're the union of countably many compact subsets. So then x is equal to the union and within the naturals of Kn and and y is equal to the union n within n of, or I guess I'm going to call it m. Do I want to be, I'll just give it a different, let's just do a different letter. Let's just do n within n, ln, where Kn and ln are compact in x and y respectively for every n within n. So sigma compact thing have anything to do with the sigma algebra and probability and measure theory? Um, so sigma compact, so in sigma algebra, the thing is that sigma is like an ordinal reference. It's not actually anything in particular about analysis or topology, but sigma is like the designator for like making a property countable. So in a sigma algebra, you have what is it? It's closed under countable unions and countable intersections. So that's where the sigma part comes in, is that sigma is just denoting how big your unions or intersections can be in the case of sigma algebra. And then in sigma compact, it's how you can express the space, right? So it's not that the space itself is compact, but I can cut it up into countably many compact pieces. You can, in general, you can, for any given ordinal, you can define that ordinal style property where like you have like omega 1 compact or kappa compact or like other things like that for particular ordinals where that designates the amount of pieces you can cut the space into, or the how big your unions are allowed to be, or how big your intersections are allowed to be. So it doesn't actually have to do anything with analysis or topology in particular. It's just a descriptor of the length of possible operations, or how fine you can cut your space into things with a certain property. So the claim then is that product of any of these two things, so Kn are compact in x and y respectively for every n. So consider fancy k. Oh, that's not a fancy k. Can we just write, there we go, which is equal to the set of Kn cross Lm such that n and m are within the naturals. Note that if U is an open cover of Kn cross Lm, or rather just a k within k, then n and m, let's see, so that U is an open cover of k within k, then how does this work? Then U, yeah, U is an open cover. of Kn cross Lm for some n and m within the naturals. So as projection is an open map, the projection onto one of these things. Oh, I don't think this works though, because when you project down open covers, you get weirdness that happens. Oh no, this is fine. This is okay. So, is this okay? Because it's just going to be the elements of U are open sets that end up covering Kn and Lm. Okay, so what I want to say is probably false, which is, okay, this is what I want to say for the sake of just writing it down, because usually when I write it down, I can figure out if it's wrong. So then the projection of U onto X is an open cover of Kn, and the projection onto Y of something, or of the open cover, right? So this should be the fancy U. Kn, and projection onto Y of U is an open cover of Ln. So, right, these are compact in their respective spaces, so there exists a finite subcover, so there exists a finite subcover in each case. Oh yeah, I'm making this way too hard. It's just a product of compact spaces that's compact. That's all it that's all it is. That's an arbitrary product of compact spaces that's compact. I don't know why I made this difficult. Um, yeah, because I don't want to, because in general, the proof is gross. You're right. I don't know why I'm making this difficult. So, so consider this. Each element I know the projection thing has issues, at least in the countably compact cross-compact case. But yes, Tikhonov's theorem is what gives you that an arbitrary product of compact spaces is compact. Um, so that is what is being used here. If we just say that Kn cross Lm is compact. So each element K within K is compact as by Tikhonov's theorem. Arbitrary product of compact spaces is compact, and since the union of Kn is equal to X, the union of Lm is equal to Y, it is the case then the union of Kn cross Lm is equal to X cross Y, and Nm within the naturals, N within the naturals, M within the naturals is a countable union. compact sets. And we're done with that part. So that's the proof part of the problem. So I'm just gonna like put this in parentheses and end this proof, or rather, instead of just ending it, just say for the counterexample, for infinite products, what you get is we can look at the integer symbol space. So consider z to the z, where, so this is a z product of just the integers with themselves. So where the topology on Z is discrete, so everything is open and closed. Topology on C is the discrete topology. Suppose Z to the Z is sigma compact. Then Z to the Z is equal to the union n within the naturals of these kn's with kn compact in Z to the Z, since projection is continuous. The projection, so pi of a kn is equal to, is compact. In a discrete topology. So pi I of kn is finite. Right, if it were not, then the open cover by singletons would not have a finite subcover, and so it wouldn't be compact, but that's not possible. So PIKN is finite, and thus the maximum over the maximum of PIKN exists. Exists for every I within the naturals, or within C. And so there's an issue here. Oh, what's the issue? It's compact, it's discrete topology, so okay, is finite, and thus this thing exists for every I within C. So suppose then, oh, but then one of these has to be unbounded, right? So it's okay, this is why I have notes. I also just, oh, the worst part about this is that usually I can construct most of the arguments for these things, and then there's usually like something where I just have to sit with it for a while. But for the sake of time, I'm just gonna have notes. Yeah, so So that's maximum exists. It is, yes, it is uncountable. Great, it is a superset of the normal like 0, 1 to the n, or 0, 1 to the z. So you can do a Cantor diagonal argument to show that it's not countable. So this maximum exists, and so define this m function, which is going to take in two integers, n and k, to be equal to the maximum of pi n of k. Finite, which we already said, yes. Yeah. This thing, and then I think I just do this plus 1. Yeah, so if x is within z, so this is just a Cantor diagonal thing, I think, right? So this is the case. Yeah, okay, yes. So if x is within zz, and x in the nth coordinate is equal to the maximum, or this m function plus 1, so I don't know that right, so this is the projection of the compact set, and so the projection of the compact set is finite, but the compact set itself is in this countable product space, so it has some like weird form where you're specifying something in an integer number of coordinates. So even though the projection only takes on finitely many values, you can think of it as like an infinite string of values where each entry has finitely many possibilities. That's still countable. Yeah, that's still countable. No, that's not countable, right? So, because if you had, so for instance, if you had a that is not what this is, to the most recent comment. But okay, so going back to the what an uncountable union of finite countable sets be countable and non-countable thing, right? So okay, so you have your infinite string of stuff. I guess I can write. I have a visual aid, so I might as well use the visual aid instead of hanging out in this corner over here, talking with my hands. Right, so this is the aside. We'll zoom super far in for this. But, right, so the reason that, so Kn is not countable, right? Kn looks like something like this. Actually, this is an example of it's a non-standard example of something that I think about all the time when I do symbolic dynamics, right? Um, so right, so you've got these spaces and there are z spaces, right? So there are z spaces, and because we said the projection onto each coordinate, so this will be p. So this particular space will be p2 of kn, has finitely many choices. But that's true for each of these integer spaces, right? So there's a diagonal argument that you can do here. As long as the projection is greater than size than 1, there's a Cantor diagonal argument that you can do here to show that Kn is not countable. So you potentially have at least one Kn that is uncountable. So saying that each Kn is countable is just false. So we can't just do that and say that it would not be, and get a contradiction that way, which is why I'm doing this thing with this maximum function. Because I want to show that this union actually doesn't hit this particular x and z. So if xn is equal to is maximum plus 1, then then xn is not within kn for every n within the naturals. Or rather, xn is not within the projection and the nth coordinate of kn for every n within the naturals, which means that x is not within k n for every n within the naturals. So the union, so x is not within the union of these kns, which is equal to the whole space. And that's where you get the contradiction. So hence, z to z is an example of a sigma compact space, or a product in infinite product. I swear math is at this level is just knowing that I need to put all of the adjectives when I'm writing down a sentence. So hence C to the Z is an example of an infinite product of sigma compact spaces. You can ask anything, but I cannot promise that I will necessarily answer anything at this time. I've been pretty good about answering particular questions, but I'm not going to like prove something if you ask me to prove it, because that is not the point of what I'm doing currently. But go for it. If you have a question, go ahead and ask. Z is an example of an infinite product of sigma compact spaces, which is not. So just to be clear, Z is equal to the union of the singletons Z, where Z is an element of Z, is and each of these singletons is compact because any open cover would contain something that covers a singleton, and you just take that as your finite subcover. So this is sigma compact. Is an infinite product of sigma compact spaces, which is not sigma compact. Oh. Career advice and planning. What particularly about career advice and planning? What to do? Then that one is done. Oh, I'm doing good. Okay, 2 in an hour. That's fine. That's like the pace that I need to have for this actual test. Oh, okay. Next one. Next one is path space stuff. Do I want to do this one? I feel like it won't hurt. It's just an equivalence relation problem. Another one of those things where it's like, you should know how to do this, but do you want to do this? Well, not necessarily. It's not. So August 2020, number 5. So on the path space, when is my qualifying exam? My qualifying exam is in a little under 3 weeks. So it'll be, I guess I could look at the calendar right here. Oh, fancy. It's right above my head. Like literally. Wait a second. Um, so not a ton of time. I've been doing this all summer, basically. Just doing these problems, and that's been my life for the past 2-3 months. So on the past space, aside from teaching, I did teach in June, but I'm not currently teaching. I'm just doing problems. So some topological space. Thanks. Let's see. Oh, the question. Let's plan a double major in physics and math. Is it doable or useful? I want to be a theoretical physicist. Okay. So, yes, dissertation work comes after the exam. Well, I mean, I'm sort of already started on my like research topics because there's a ton of background reading for them, but I haven't like touched a problem or proved like an original lemma yet. So I'm not there. The dissertation work and hopefully more research stuff is coming in the future. That is not necessarily directly related to my dissertation. So double majoring in physics and math, usually that's very doable because a lot of times math courses and physics courses overlap a ton because you need a particular amount of math in order to for prereqs for physics classes. So usually it's not hard to do a double major in physics and math. For theoretical physics in particular, having a good math background is helpful because a lot of times once you get deep enough into theoretical physics, a lot of the stuff you're doing is like math light, where you're making mostly rigorous arguments about things. Um, and there may, yeah, I don't know. There's some like weirdness there that comes in because the physicist's definition of rigor is different than the mathematician's. At least that's what I've heard, and that's what I've seen uh, when I've done research with some people that are more physics oriented. Um, so So on the path space, this it's just I don't understand why they used fancy P. But fancy P is what they wrote down on this exam. So I'm going to use fancy P, even though it should be the power set. But this is the path space of some topological space. Oh, if I could write this morning, that would be great. X. So this is going to be, this is equal to the set of paths such that, right, gamma is continuous. This is a terrible color to do this in too, especially when I'm having a trouble writing. Um, Define then gamma 0 is related to gamma 1 if and only if do there is a continuous function. Big gamma, which goes from the square to x such that gamma of, what is it? It's gamma of 0t is equal to gamma 0 of t, and gamma of 1t is equal to gamma 1 of t for all t within 0, 1. And then show that this is an equivalence relation is the problem. So prop show that tilde is an equivalence relation. So in my brain, from like knowing what loop groups are or like the fundamental group, this is like the most algebraic topology I've seen on a problem, other than like the like categorical category theory-esque stone check compactification problems that come up on this test. But also it's like it's sure that something's an equivalence relation. So in theory of it is not super deep. It's like just what is an equivalence relation and then use this definition to show it. So nothing too crazy happens in this problem as far as I'm aware, or as far as I remember from doing it a week or two ago. So proof, reflexive. Well, reflexive the hard one. So like let gamma be a path, then I'm not by any means a physicist, so I have a lacking understanding of what would be a good answer there. Most people that I know who pursue physics are like really into linear algebra and diffie-q and partial differential equations and that realm of things, but I'm sure that there's other math that applies to physics as well. Because I've seen a lot of people talk about physics and abstract algebra in more of the theoretical math world and theoretical physics overlap. But I don't really know. That's all I got. So gamma be a path, and I want to show that there is a function, so it's just constant in one variable. So then consider gamma, which goes from 0, 1 across 0, 1 to x. I usually do Pomodromo when I am studying, but for these exams, just because I think these exams are more about the, like Pomodromo is good because it like is rehearsal based, right? But I think these exams are more of like a stamina thing. So I'll usually so for studying for these, I try to do as like many problems as I can in say like 2 to 4 hours, and then I take a break for either the rest of the day or I'll take like a 5 or 6 hour break, and then I'll do another 2 to 4 hour session and so it's like simulates taking one of these tests because balls are probably the like most mentally draining thing I've ever done in my entire life. Uh, well, that's not necessarily true. Working in IT was one of the most mentally draining things I've done in my entire life. This is like a is not a close second, but it's like in terms of stress that comes from the thing itself, it's pretty high up there. Do such that for every what's my yeah my path variable is first coordinate for every s within 0, 1 gamma of s t or yeah gamma of st is equal to gamma s of t. The prop is that this is continuous, so the proposition is that this is continuous POC is that or rather claim is that gamma is continuous. And I think this is the only hard part of this problem. Because once I know that this is continuous, I can do everything else. So yeah, so let well, okay, let's do it this way. So note that gamma s of t is continuous. So for any open set, well, that's an Oh yeah, this is fine. So for any open set U subset of X, gamma S inverse. Oh, and I need to just, I don't know what I'm doing. It's just gamma of T. Note that gamma is continuous. So gamma inverse of U is open in 0, 1. That's a very, that would require quite a long time to explain all the differences between those areas. There's a lot of intersections too, so they're by no means disjoint areas of mathematics, but um, they do focus on different things. Most of which I am not necessarily the best to comment on because a lot of the stuff that I do falls outside of those particular types of topology because I'm more of a I've more focused more on symbolic dynamics and symbolic representations of dynamical systems and complex dynamics um, than those specific areas of topology, and then geometry is its own thing in some sense. Geometry is a very weird. Geometry is one of those things where I don't know exactly how to explain it once you get to a high enough level. There's the whole like, oh, you work with triangles and just find the triangle that you get in high school math. But there's some weird stuff when you mix algebra and geometry where you have this new interpretation of what geometry is that I don't fully understand. But I think it just might be that I don't have the intuition for that. It's not that super intense. Sure. So gamma is continuous with the gamma is it's okay. Oh, I need to. I'm right and sloppy, which is okay. It's just could be worse. There we go. So proof of claim. So note that gamma is continuous. So for any open set, U subset of X, gamma inverse of U is open in 0, 1. So as so and since how do I want to say this? So now consider gamma inverse of U. Well, then gamma inverse of U is equal to, it's just X cross gamma inverse of U. That's what I want to say, but that's not rigorous at all. Because no matter what I put in, I'm going to get, that's what I want to say it is. I have an open set in the image X. X is the image space, so gamma inverse U is open. So then gamma inverse U is going to be equal to, well, what does it do? U is stuff in X. It's the stuff of, yeah, because when you pre-image, it's based on the target set. So I'm not changing the target set when I do U inverse, gamma inverse of U. So then X is within gamma inverse of U if and only if gamma or this is xy. Let's do it that way. Or st. Let's do st because that's what my parameter space is. If and only if gamma of st is within U, but that means that gamma of t is within U. Which means that t is within the pre-image of U. And it's independent of S. So this and S just needs to be within X, right? So S is within 0, 1. Yeah, not S is within X, but S is within 0, 1. So S is within 0, 1, and so this is if and only if T is within the pre-image of U, and S is within 0, 1, which is if and only if S and T is within gamma. S is the first. S is first, so it's going to be 0, 1 cross. Yeah, so I wrote it weird. I think I wrote X cross something, and that's why it was weird. So this will be 0, 1 cross gamma inverse of U. So that's open, which is open. Which is open. So gamma is continuous. And gamma is related to itself. Cool. So that's reflexive. And next, symmetric. Let X related to Y, or not X and Y. They're gamma and gamma naught and gamma 1. So gamma naught related to gamma 1. Then there exists a gamma which goes from 0, 1 cross 0, 1 to X such that gamma of 0 is equal to gamma of 0t is equal to gamma 0 of t, and gamma of 1 t is equal to gamma 1 of t. Then consider how do I want to do this? Gamma of f of st, where f of st is equal to, it's just going to be 1 minus s and t. Note that f is continuous. Continuous. So gamma prime equal to gamma of f. Let's do it that way. So I can write gamma of f, or gamma prime, or I can write gamma prime instead of gamma of f all the time. Gamma of f, where f of st is by definition equal to 1 minus s and t. Note that f is continuous, so gamma prime is continuous, and gamma prime of 0 is of 0t. Gosh, I do that every time. So gamma prime of 0t is equal to, well, this will give a 1t, so it'll be gamma of 1t, which is equal to gamma 1 of t, and gamma prime of 1 t is equal to gamma of 0t, which is equal to gamma 0 of t. And so that finishes symmetric. And for transitive, so transitive is not hard either. So let's gamma related to gamma 1 and gamma 1 related to gamma 2, then there exists a gamma 0, 1 and a gamma 0, 1, 2 from 0, 1 cross 0, 1 to x such that gamma 0, 1 of 0, 1 or 0t is equal to gamma 0 of t. Gamma 0, 1 of 1t is equal to gamma 1 of t. Gamma 1, 2 of 0t is equal to gamma 1 of t, and gamma of 1, 2 of 1t is equal to gamma of 2t. Then consider gamma 0, 1, gamma 0, 2, which is by definition equal to, I don't want to do this. I want it to be that gamma gamma of 0, 1 of st 0, 2 of st if 0 is less than or equal to s less than or equal to 1/2, and gamma of 1, 2 of st if and only if, oh, I need to be careful here too, because I want to make sure that this thing starts at 0 and goes to 1. So it's going to be something weird with s. So it's going to be just 2s t, and this will be 1/2 is less than or equal to s less than or equal to 1. So this one will be 1 minus 2. Oh, it's going to be 2s minus 1. Right, because at 1/2 you get 0, and at 1 you get 1. Okay, cool. So then gamma of 0, 1 to st, gamma of 1, 2 to s minus 1 t are continuous. Well, is a composition are compositions, because it's two different things. Of continuous functions which are continuous and as gamma of 1t is equal to gamma of, so 0, 1 is equal to 1, 2, and I'll put a 0 here, 0t, at s is equal to 1/2 by the pasting lemma. Pasting lemma, gamma of 0, 2 is also continuous. Hence, gamma naught is related to gamma 2. And then do I have room? Do I just, oh yeah, I have room for another problem. I think I know what it is. Yeah, I think the next one's going to be weird. So Gamma 0 is related to gamma 2, hence tilde is an equivalence relation. And we're done. Okay. Oh, cool. So that one's not terrible. It got split, but that's okay. So that one's just, I think the hardest part of this one was the reflexive part because you have to justify that the gamma that's just a constant curve is continuous. So the pasting lemma for continuous functions is a topological lemma that's used to say that piecewise functions are continuous if they agree on the intersections of their domains, right? So in R2, right? So it's just, right? So it's the natural thing. The intersection of so this, if this is function 1 and this is function 2, the only time that they would be continuous is as if they meet up in their intersection. So if this is the intersection of the domain F1 intersective domain F2, you need to be able to paste together the functions, and the only way that you can paste together the functions is if on their domain they are the same on the domain, so on the intersection of their domain. So must be same function intersection of domain. So there's also so I know that it's I think I've heard of it in those areas as well, but for topology, general point set topology, the pasting lemma refers to how to combine continuous functions into other continuous functions on a larger domain space. Hey, oh, which one is that? Oh, that was on Twitch. So, um, yeah, so it's for any topological space. I can pull out where is it at? It's, do I have my book over here? I don't have my book over here. It's in Moncrief's. Moncrief's has a definition of has a proof of the pasting lemma inside of it. So Moncrief's topology, and then you can prove it in general so the pasting lemma, right? So this is the finite version of the pasting lemma, because you only have two functions and they agree on their domain where their domains intersect, which is at s is equal to 1/2. But there's a infinite pasting lemma where you have to make sure that the domains that you're working on are all open sets or locally finite sets. So there's like variations of it as well. It's not just metric spaces, because you can also apply this to like showing that the Sorgen-free line and the Sorgen circle are homeomorphic to each other. Both of those are not metric spaces, but you can show that they are homeomorphic to each other by using this idea. Anyway, I'm going to get rid of it because I want to do another problem in this area. So got one more, I think. Like, it's already 1:45, so if I can do this, this will be probably the last problem I do today, and then I will skedaddle. Because 2 hours usually is like a good time to cut off these streams, and then I'll probably do something later tonight on Twitch when I'm done with work and other things that I have to do in order to survive outside of being an entity on the internet. So this is 2020, number 6. This is a problem that I think is really cool, honestly. But I always have trouble with it, the first part of it. So it's prop. Oh, brighter. That's brighter. Okay. Show that a connected separable metric space is a singleton or of cardinality continuum or of size of the size of the continuum. That's not how you spell continuum, Nathan. Continuum. Okay, so how does this work? Um, the proof. It's not a great color. I should just do classic yellow, just for the heck of it. So proof. So suppose first that that X is a connected separable metric space and suppose that X is countable, or rather that it's size less than C, or the size of X is less than that weird C that they use for continuum. No, not really. It's a little weird, right? So you have to be careful. So continuum means that you can be put in bijection with the reals, I guess is one way of saying it. Uh, you don't, there are uncountable infinities that are larger than, well, okay, it's weird because then you get into like things that like yeah, so there are, I'm gonna say for the sake of doing this problem, I'm just gonna say in bijection with R, uh, but you could get more technical with it and work with cardinals and ordinals and things and do some weird stuff if you want to, but I'm not going to. Uh, there are definitely uncountable infinities that are larger than the continuum as well, because the power set of R is such a set. So so suppose first that X is a connected separable metric space, and suppose that X is countable. Well then, note that for any X within X, the function yeah, so then note that for any X within X, the distance between X and so it's basically like you're using X to define, so an X within the space to define a map using the distance function. So where D induces the metric topology on X. That just means it's a compatible metric. So D is a compatible metric, then for do this. Yeah, so it's a continuous function. It's basically what I want to say. So then for AB subset of R, the pre-image of that thing of AB is equal to the intersection of, well, the ball of radius intersected with the complement of the closed ball, so intersected with the set of x within x, such that the distance between x and A is less than or equal to, or x and, I need to use a different letter. So y within x, distance between x and y is less than or equal to A complement, which is open. So d of x dot is continuous. And the continuous image of a connected set is connected. So, and d of x comma dot of x is connected, yet d of x. So, and thus d of x dot of x is connected because continuous image of a connected set is connected, yet d dot x is countable. So there does not exist an inner subset of dx dot of x, which is a interval. Because every interval is strictly larger than that set. So this thing is not connected. Unless it is a singleton. Because a singleton is trivially connected. So thus, the size of x may be equal to 1, or the size of x is greater than, it's greater than a countable set, right? So it's greater than the size of the naturals. That's what I want to show, right? It's, yeah, so it is exactly 1 point or exactly z points. So it's strictly greater than the size of the naturals. Now suppose I guess I suppose that it was countable, right? So this is in the case where we're still countable, right? Because I said suppose countable, right? Yeah, suppose first the x is connected separately in metric space, and suppose the x is countable. Yeah. So then thus x is equal to 1. Now if x is not countable, suppose then that x is larger in size than the continuum. So x has more than a continuum number of points. So what do we do with that? Since x is separable, so there exists d subset of x countable and dense. Oh, I know what to do with. I know it has to do with separability. Where are we? Okay, I think I know what to do. Um, so there's the d with an x countable and dense. So I'm going to zoom in even farther because I want to not have to. I'm already super zoomed in, but I want to have to not go on to another page. So let's make my pen smaller. All the way up, and let's turn down farther. So, oh, that's not helpful. Just, okay, consider the set of dx comma a. That's not what I want to do. I want it to be, there's a set of distances. So I want it to be, it's just d of x comma d, right? Which is equal to the set of dx comma a such that x is within x and a is within d, which is a subset of R. Okay. But I don't want these. I want all of the ones that change with A. So I want it to be some, I guess, fancy D of D is going to equal to the set of sequences of distances, because this is separable, so this is countable, so these things form sequences. So it'll be D of X comma A, such that A is within D, such that X is within X. And suppose that X, or there exists an X and Y with an X such that, okay, well, first things first, right? So each of these distances, right? Each of these things is within, let's do a different color. So each of these things is within R. So each of these sequences is within R to the N, which is still a continuum amount of points. Right? So the number of possibilities in this thing are a continuum number. And I know that I'm supposing that my space is bigger than a continuum. So if I can form an injection from my bigger than continuum thing into this continuum sized thing, then I will get a contradiction. So, right. So suppose that there exists x and y such that these sequences, the distance between x and um, a within d, and does not equal the distance between I want it to be equal because I want them to be distinct, right? So I need, so such that x does not equal y, and And these sequences are equal between y and a within D. Then there's a triangle inequality issue. So the distance between x and y is going to be less than or equal to how does this work? All right, so then there exists a b within D such that the distance between x and b is going to be equal to the distance. Hey, hello. How's it going, Michael? Thanks for stopping by. I'm having my daily anxiety attack about this test, but that's how that's going. I'm almost done with this stream, but thanks for stopping in. So there's a b within D such that the distance between x and b is equal to the distance between y and b, and this is going to contradict the triangle inequality. So this is supposed to be less than the distance between x and y over 2. Yeah, because so triangle inequality is just distance between x and y, so distance between x and b plus y and b. So this, yeah, just I'm going to write it down. I'm going to erase it for my own sanity. So distance between x and y is equal to the distance between is less than or equal to the distance between x and b plus distance between y and b. And these two things are equal, so you get a 2 there, and you can divide both sides by 2. So these things should be greater than this. Right? Did I do this backwards? I think I did this backwards. So the distance between x and y is less than or equal to the distance between x and b plus the distance between y and b. Oh yeah, so it's the distance between x and y over 2 is less than or equal to the distance between x and b. And oh, it's because, okay, I'm using two different things here. So two things I'm using is first off is that separable, so D is dense, so I can find a point in D that is as close as I want it to be to x and y, because all of their distances agree for D. The distance between x and y is fixed, so I can find a B within the dense set that is less than the distance between that fixed distance between x and y over 2. But then by triangle inequality, this will be less than or equal to the distance between x and b, what I just wrote earlier. So distance between x and b plus distance between y and b over 2, but these things are equal to each other in the numerator here, so this is just one of them. And this is a contradiction. Hence, the size of x should be continuum or x is equal to 1 as desired. Hey, okay, squeezing it in. So this definitely went smoother than the last 2 times I've done this, and that's good. I need to go and do other things today, like eat and just make my apartment look decent, and I have to go to school and do some particular upkeep things because I get to teach calculus this fall for the first time, which will be fun. So thanks for stopping by. I appreciate hanging out with me as I work through problems. I will be probably on Twitch doing more problems this evening, probably around like uh, 7 or 8 o'clock. And I'll do that for a couple hours tonight because I just need to study more. Because it's gonna happen in a few weeks, and I'll either pass it or I won't, and I'll be fine. So that's all for me. I will see you around on the internet when I see you, and hopefully when this test is over, I can go back to doing just normal chalk content things that I, or being creative with video like I usually enjoy to do. So, see ya.